right, good morning. I trust you all had a refreshing swim this morning and you're ready to do some work. This will be about computational social choice. My name is Ulle. I have unfortunately not been here on Monday, so I missed all these little introductions, so I don't really have any clue who's in the room right now. I know 2 or 3 people, but I'm not talking to them, I'm talking to the rest of you. So I wanted to check first a little bit of what people's backgrounds are. So who would say that they are doing computer science very, very broadly? All right. And so I would say I'm a computer scientist, but a lot of what I will talk about today and what I do in my daily life is economics. So do we have anyone with a somewhat economics background? Still a few, very nice. Yes. Psychology doesn't count, I think. Then we have a bit in between, so operations research. You have this decision thing in France that I think some of you are doing. So who feels that they have that kind of background? Yeah, sometimes it's a bit of both, right? Yeah. Mathematicians. Yes, should be all right for you, I think. I don't know. Philosophers would be nice, but I fear not today. There was a philosopher? No. Anything else that I follow? Psychology and anything else? Was this argumentation theory? So but you probably do that within AI, computer science. Yeah. So I guess a lot of you of the computer scientists are doing AI. So within AI, what are the main areas? Machine learning, any kind of machine learning, who's doing that? Yeah, could have been much worse. I mean, could have been many more of you. Maybe knowledge representation, this kind of thing. Like, okay, very nice. What else do they do in AI? What else do they do? Natural language processing, computer vision, robots. Okay. Planning, yes, planning. All right, you found your way here, very good. Okay, good. So it gives me some rough idea. So let's first say a little bit what computational social choice is. So are there any people in the room who are maybe starting a PhD on ComSoc and they have a rough idea of what this is? So who's a little bit in, so you will not learn a very much new stuff today, maybe tomorrow, I hope. This is mostly for the other people. So what is computational social choice? So first of all, what's social choice theory? That's the art and science of collective decision-making, a little bit how people do take decisions, but mostly how they should take decisions. What would be the right way of doing this? It's very closely related to game theory and decision theory. So these are kind of 3 branches of mathematical economics where social choice theory is one of them. So decision theory is more about what should one agent do and why and maybe how. Game theory is like you have your own utility preferences, but there are other people in the world, you have to react to them in a strategic way. That would be game theory. And social choice theory is looking at from above at all of these agents acting in a decision theoretic and game theoretical way and trying to design an overall system that's somehow good, maybe gives us some fair outcomes and stuff like that. So that's social choice theory. It's traditionally studied in economics departments. Maybe very, very traditionally, it's political science, like how do we take decision in politics, and the economists have made it a formal enterprise and really taken it over in the middle of the last century. Of course, it involves a lot of mathematics. It also involves philosophy because you have to think about, what is even fair? Why should we do it like this? And then a mathematician would say exactly what that means. And more recently, maybe in the last 20 years or so, computer scientists have started getting involved as well because whenever we are taking these decisions according to these fair ways, we have to somehow get it done. It might be algorithmically difficult to do that. So that's a very natural computer science problem. It's relevant to many applications. I've listed some of them here. So one is related to what you heard about yesterday, at least, and maybe on Monday, I don't remember, about fair division. How do we allocate resources to people in a way that's fair? I would say that's also part of computational social choice. Next example is voting. So we have to elect a president. Everybody gives their preferences. How do we aggregate these preferences to decide what's the best person to fill the shoes of the president? But also things like we have different judgments about what's true and false. And the classical example in a court of law is who is guilty, who is not guilty. How do we aggregate these views of the different agents to come to an overall view? So the examples I've given you now are really from society, like real people taking real decisions, but they're also always counterparts very much in core computer science. So for example, instead of aggregating the preferences of people about who should be president, we could also aggregate the rankings of several search engines about what's the most relevant web page to our query. And then this process of aggregating these different rankings is mathematically very, very similar to the process we take when we run an election. And one of the things in computational social choice is to understand these parallels, see where they maybe break a little bit with these parallels, and try to understand both of these things a bit better. So taking inspiration from the work the economists have done already and see whether we can apply this in computer science, but also have an original view on these problems, maybe driven by more computer science specific problems to enrich the theory as it is practiced in economics. All right. Why is this AI? I think it's a fair question. It's not, I could teach this in the economics department. I would also fit perfectly well what I'm doing today. So why is this part of AI? Basically, it started, I would say, in the late, maybe mid-1990s that multi-agent systems became more and more an important and popular topic, that people realized it's not just about building one system that's artificially intelligent. It's probably more realistic to have many small systems that are somewhat okay in what they do in terms of AI, and they interact with each other. And we want to harness the power that comes from these systems cooperating with each other, competing with each other. And then people realized that somehow economists had studied very similar problems for a long time with people cooperating and competing with each other, and we should lift some of their ideas, move it into AI. So that's why these economic paradigms like game theoretical ideas, social choice theoretic ideas have become part of AI. So that's the original reason why this entered the field of AI. And I've put here a bit of this, what's called the 100-year study on AI, which in 2016 was a large group of important AI researchers, a bit US-centric, but I think they still did a good job. They tried to identify what are going to be the important topics in AI in the coming years. I'm not sure whether they really meant in the next 100 years, but there's another number that shows up until 2030. So for the next 15 years when they wrote it. And they identified 11 hot topics at the time. I've put them here. So there's the usual machine learning stuff. So you would expect that. Then there are kind of robotics, computer vision, NLP. So the most obvious examples of AI, I would say, where you can really see there's something's happening that looks a bit like what humans do. So of course, that continues to be very, very important in AI. There's this neuromorphic computing, which I don't know what it is, but then all the rest, I would say, fits under multi-agent systems like crowdsourcing, algorithmic game theory, computational social choice, human computation, collaborative systems, Internet of Things. So they're all about different agents interacting with each other to get a better result than we would get if we just were to design a single agent that does this job for us. And algorithmic game theory and computational social choice, they're kind of the most abstract foundational topics mentioned here. So it's very basic stuff. You don't always immediately see the robot playing chess on Mars and talking about it in Chinese coming out of this, but it is somehow doing something very basic that many people consider to be relevant for AI. So even if you're working in a different area of AI, I think you can maybe take out some ideas from this for your own work. Okay, what I will do in this tutorial today and tomorrow is I will start today with basic voting theory. So this is very classical stuff. What's the right way to take a decision when there are different people involved who may have different preferences? Most of what I will show you is from the 1970s and before, but I will occasionally have a few hints here and there about more modern ideas. But it will be just to teach you this basic stuff. And then tomorrow we're going to use that in a much more obviously AI type of thing. And we're going to talk about how can we automate some of the reasoning about these voting scenarios. And we're also going to talk about the notion of explainability, which has become very, very popular, specifically in the machine learning domain, because there it's really, really needed. Otherwise, things are not going so well. But that idea, of course, is very general. We want anything, any decision that a computer takes to be explainable. And that's also relevant to social choice. I will talk a bit about that tomorrow as well. But today will be very much foundational stuff. If at any point you have any questions, objections, or just you would like to talk a bit yourself, it's completely fine to put up your hand and ask. If you don't ask questions, actually, independently of whether you ask questions, I will ask you some questions. So there will be some exercises on the slides. So please be prepared for that. Okay, so let's start with an example. We are going to deal with situations today where we have some agents, and the number of agents will always be n, maybe 3, maybe 5, maybe 100. And we have some alternatives. The number of alternatives will be m, and we have to choose one of the alternatives. And each agent has a preference about the alternatives, and we're going to think as this preference is about a strict ranking from the best all the way down to the worst alternative. And that's the input to our problem. So everybody gives us their own ranking of the alternatives from best to worst, and we have to come up with a voting rule that takes such inputs and produces the right alternative for this group of agents today. I have put 3 examples here for voting rules that are sometimes used. One is the plurality rule. There we're gonna ignore most of the ranking and just take the top in everybody's rankings, and we give 1 point if it shows up on top. We add up all the points, whichever gets the most points wins the election is chosen. Plurality with runoff is very similar. We initially just look at the top alternative of everybody's ranking. We add up the points, we keep the 2 top runners with the 2 most points, and then we're gonna look again at everybody's rankings and we just compare those 2 and see how many people say A is better than B and how many people say B is better than A. And the one that wins this majority contest wins the election. And the last one is the border rule. Here we, for example, let's say there are m alternatives. We give 9 points for the top spot, 8 points for the next one, then 7, all the way down to 0. We add up the points. Whoever wins the most points wins the election. So do you know of any real-world elections where these rules are used? First exercise. Presidential election, all 3 of them, one of them?
First ones.
The 2 first ones. So what do you mean exactly? Where is are they used in different countries or? Let's only take France as an example. I completely agree with that, yes. So what do they do in France? Which of the 2 is it that they actually do it using? Well, this kind of is already built in. So I would say in France, people use this, yes. Is it good? Is it bad? Medium? It's widely considered bad, but is it maybe a bit better than this one, which they use in many other countries? I'm not sure. Maybe it's still a bit better than this one, right? So this one is, I mean, there are lots of little tweaks in specific countries, but that's maybe the most common rule. Just say what you want. The one that gets the most votes wins. We are putting very little information here about what the agents want into the rules. So we shouldn't be surprised if we get a somewhat weird outcome. We're doing a bit better here. We're asking for a little bit more information, but there's still, most elections in France, things happen that, maybe a bit questionable whether that's really what you want. And about border, anyone knows of any examples where border is used? Yes?
Guys, the Eurovision contest.
In the Eurovision contest, there is a variant of border. It's not exactly these points, but it's like, what is it, 12, 10, so 12, 10, 9, going down to 0, and then a lot of people with 0. So it's something very similar to the border rule. It's not exactly these points, but very similar. They are very good. So I'm not aware of big political elections where the border rule is used, but it's actually very, very popular in kind of medium important elections. So if you have like some professional society of, electrical engineers or something, probably they're going to elect the president with the border rule. So this is very, very typical. So it's used in practice. All of them are used in practice. Okay, so talking about practice, let's do an example. Imagine you are at a meeting similar to this, but there are just 9 people. And we have to vote on what drink will be served for lunch because it's too complicated. Everybody drinks their own stuff. We don't have enough time, so you have to choose one drink. There are 2 Germans, 3 French people, and 4 Dutch people here. You all know about the Germans. I guess you heard about them. So they would like beer if possible. Next best would be wine, and milk would be weird. Some of you may also be familiar with the French preferences, so they would think wine is a better choice than beer. And again, they would think milk is a weird choice. The Dutch, maybe you're not so familiar with. It's a small country close to Belgium where I work and live. And the interesting thing, this is not made up. If you go there and you have a business lunch, they will serve milk. Maybe 2 types of milk, but it will be milk. No water, no anything else. So the people who have gone up there, that's why they are so tall. They like milk the most, and then maybe beer and then wine. So how do you choose? Not everybody will be perfectly happy. Some people will be maybe very unhappy. Which drink, these are the alternatives, would win under the plurality rules? Any takers? The beer, plurality. Which one was the plurality? Was the first rule on my previous slide? No one? No. I made an example where there are no ties to make it easier. So plurality is not the French one. It's the easy, it's the simple one. It's just go for the one that gets the most top ranked choices. Milk, exactly. So there are 4 people who want milk. There are only 3 people who want wine, only 2 people who want beer. So milk will win under plurality. What about if these were French presidential election candidates? So what if we were to use plurality of runoff? What would win?
Wine.
Wine, yeah. So what would happen in the first round? Somebody said there, the Germans are eliminated. Let's say the beer is eliminated. So wine and milk make it into the runoff. And then the Germans will support wine rather than milk. So it will be 5 against 4 in the final round. So wine will win. And then for the border rule, imagine you had to design an example like this. What would you hope that the outcome would be for border? Beer. And is it beer? Is it beer? It is beer, right? So let's just check. I think milk is clear, has no chance under border. Here, it would be 2 + 2, so 4 points. And then 7 more points, so it would be 11 points for beer. And for wine, it would be, I'm confused now. No, yes, it would be 6 + 2 would be only 8 points. So yes, and milk would be even worse. So we have 3 different rules electing 3 different outcomes. All of these rules are used in practice. None of these rules is totally crazy. You can give reasonable arguments why you might want them. So what do you do? Right? So that's why there is something like social choice theory. It's not enough to just invent a rule. You have to think a little bit about it. What would be good? So how can we choose a voting rule? There are different arguments we could use. The first ones are normative arguments. We might say, oh, this rule is really fair because it has this nice property. So we can try to formulate properties we care about, make them precise, and then prove this rule has it, this rule doesn't have it, things like this. That would be the normative approach. That will be what most of today will be about. But I want to at least briefly mention that there are other ways we can choose as well. There are epistemic arguments we can use. So that means, imagine there is an underlying ground truth. There's really a best alternative. I'm not sure the drinks example is a good choice. Well, maybe there's objectively the one that's best for your health or for your happiness or something like this. Maybe somewhere in nature, this is known. Just we, the voters, we don't know it exactly. So can we use, but we give noisy estimates of what we think is the right thing for us. Can we use the rule to tickle out somehow what would be good for this group of people? And maybe some rules will do a better job than others in doing that. So that would be epistemic ideas. Computational requirements. Maybe some rules, not the ones I've shown you, but some other rules could be really, really complicated and maybe have very nice theoretical properties, but would be really hard to use in practice. And maybe we don't have enough time for application. So we care about computational requirements as well. And the last one are informational requirements. So I said that already. The plurality rule, for all its faults, is very nice in the sense that it needs very, very little information to take its decision. You just have to tell you, this is what I like the most. Nothing else about my ranking. So that in itself is a good thing. And you may want to border uses a lot of information, maybe too much, some people would say. So how do you choose between these things? But what I want to focus on is the normative part. And this is called the axiomatic methods. So these normative requirements, things that we care about, they're called axioms in social choice theory. And so what we usually do is we first think about, more philosophically, if you like, what would be a good property that I care about? Maybe ethical things or things that come directly from the application domain. This is really an important feature I care about. I try to write it down. I try to make a definition precise. So there I'm going to use some mathematics, maybe even some logic to very precisely say, what do I really mean by this? And then I'm trying to prove results about it. For example, this rule has this property, that rule does not have this property. Maybe this is the only rule that has this and this and this property. So if I'm convinced you that this and this and this property are good, I have convinced you that you must use this rule. Or maybe negative results saying, I would like this and that property, but it's mathematically impossible. Then no rule exists and I can prove it. That would be bad news, but it would be good to know, right? So you can do these kind of things. So what I will do for much of the rest of today, I will show you examples of using this axiomatic method. A lot of it example-driven, just a few examples of axioms, a few more examples of rules that do not satisfy these axioms, but I will also have a couple of actual theorems that really say something deeper about these kind of things, mostly in the second part of today. In most cases, I will try to keep the slides light, so I don't have formal definitions of these axioms on these slides, but a very important part of this field is that everything can be formalized and has been formalized. And one place of looking it up is the paper at the bottom, which is kind of a survey paper of this area. And there are many other places where you can look up these things as well. All right, let's start. Here are a few examples for axioms. Properties of a voting rule that you would like to see satisfied. The first one is the participation principle. It says it should always be better, or at least as good, for a voter to show up, to participate in the election and cast her truthful ranking, a truthful preference, than to not vote at all. Right? Later, we're going to talk about, okay, sometimes it's good to lie about your preferences for strategic reasons. I'm not even talking about this. I'm just talking about it's better to vote truthfully what you want than to not vote at all. You would say, obviously, I want that. How can any voting rule not have this property? It would be crazy. So yes, it's a very fundamental rule, that property that we really would like to see satisfied. The next one is the Condo Say Principle. It says, in those cases where there is one alternative that would beat any other alternative, if you were to just ask the voters about those two in competition, then we should elect that alternative, right? There will be cases where there is no such obviously good alternative because it's more complicated. But in those simple cases where there's a clearly, obviously nice candidate, nice alternative that would beat anybody else in a majority contest, our voting rule should agree with that decision. And in the other cases, it should do something else. But in those cases, it should agree with that decision. Another property that we might care about. And the last one is the Pareto principle. I think that's the best known of these. It says, if I have two alternatives, let's call them X and Y, and every single voter says X is better than Y. Not necessarily X is the best, but X is somewhere in their ranking better than Y. Everybody agrees on that, and on the rest, but I don't know. Then Y should not win because it's dominated by X. Doesn't mean that X should win, maybe Z should win, but Y for sure should not win, says the Pareto principle. So these are very, very basic properties that we hope will be satisfied by our voting rules. And what I will show you on the next 3 slides is that no, it's not so easy. They are violated. Some of them are violated by quite natural choices of rules. Okay. The first one is the participation principle. So that was the one, it should be always in your best interest to just show up and vote what you really think rather than staying at home. Plurality with runoff, the local rule used here to elect the local president, does not have this property, as we're seeing now here in this example. So here it can happen that it's better for you to just not go to the election, which is weird. Okay, let's have a look at this. So this is also called the no-show paradox. It can be better to not show up. So suppose we're having an election like this. So there are 25 voters who say A is better than B, better than C. 46 who say C is better than A, better than B, and so on. Let's say this is what people really think in their mind and how they would vote if they were all to show up and just be truthful about what they want. So what happens under plurality with runoff? A and C make the runoff. These are the two better ones in the first round. B gets eliminated. So these 24 voters in the second round have to choose between C and A. So they will go for C. So there will be a very big majority, 70 against 25, who in the second round say C is better. So C would win the election. So that would make the first group very unhappy. Let's keep a note of that. So C wins the election. The first group is really unhappy. They would like A. Probably they're not going to get A. And even B would be better than C. So now imagine that 2 of the voters of the first group of these 25, they instead stay at home. So there are only 23 of them showing up. And we run the same election. So everything stays the same. I just changed from 25 to 23. What happens in the first round? In the first round, yes, very good. In the first round, C and B are making the runoff. So these 23 people, then they can't get A. So in the second round, they have to choose between B and C. They like B more. So in the second round, we get 24 plus 23 is 47, which is 1 more than 46. So nicely designed example. Just about B wins in the second round. So now in the new election, with 2 fewer voters, instead of C winning, we now have B winning, which those people who stayed at home prefer. So those 2 people, they made a good choice to stay at home in this very specific situation, and they got something better for themselves than if they had voted for what they actually want. That's very, very weird, but that's a real thing. So that's a problem of the election rule here. All right. Another example. So this is what the Condo Say Principle. The Condo Say Principle said that if there is some really nice alternative, so that every other alternative would lose to it in a direct majority contest. So if you only ask about this supposed Condo Say winner against another alternative, the Condo Say winner would always do a little bit better. And maybe it's a different majority each time, but it would beat all of the other ones in one-to-one contests. In those cases, we should elect this Condo Say winner. Our voting rule should do that. So let's see about the border rule, whether it has this property. And you can see from the title, it doesn't. So suppose there are 11 voters with these preferences. The border rule elects B, it says. Let's just check whether that's true. So we get, right? So we get 2 points if we're here, 1 point if we're here, 0 points if we're here. So we just have to add them up. So 4 plus 6 is 10, plus 4 is 14, plus 0. So it's 14 for B. A has no chance, it's clear. So let me not add up the points for A, but let's do it for B just to be sure. B would be 4. For C, sorry, we just did. So let's do C, very good. So it would be 8, nothing here, 10, 12. So it's less than 14. So I think I'm right. B wins the border election. So the border rule will elect B. That's why I called it B. So why did I call C C? What do you think? Because it's the Condo Say winner. Let's check whether it really is the Condo Say winner. Would it win against anything else in a pairwise majority contest? Let's first try C against A. So there are 4 people in favor, 6 people in favor for C against A, and only the other 5 A against C. So yes, C beats A in a majority contest. What about against B? There are 4 people who say C is better, and then there are another 2 people. So there are 6 people who say C is better, and the other 5 say the other way around. So again, C beats B in a pairwise majority contest. So it is the Condo Say winner. So the Condo Say principle, the axiom says you must elect C, and the border rule says, no, I'm going to elect B. So the border rule does not satisfy this property, which is very strange, right? So it's a convincing rule. It makes a lot of sense. Smart people really like it. A smart person proposed it in the first place a couple of 100 years ago, a bit more. And it doesn't have this very basic property that is like, C is so good, right? Whenever we elect anything else, people say, oh, but C is better. So it's crazy to elect anything else, but the border rule sometimes does it. So that's a problem, right? So if we really care about Condo Say, we can't use the border rule. And one more example. So these is a whole family of voting rules that I'm sketching on the slide here, so-called cup rules. So they're, for example, used in a football tournament. If you like, something like this is used in a football tournament where you have this binary tree, you put the teams at the leaves and they play against each other and somebody wins. We can also use this as a voting rule. We can draw a binary tree. We can put the alternatives at the leaves. And in any time two of these teams of these alternatives meet, we ask the voters, who do you prefer locally between those two? And that one advances to the next stage. So this tree then represents a voting rule. It says, to make your decision, first compare B against C, whichever is better, compared to A, whichever of those two is better, compared to D, whichever of those two is better, wins the election. That's the definition of the rule. And on the right-hand side, I have an example for a profile for preferences of the agents. So there are 3 agents, 3 voters, Anne, Bob, and Cindy. And these are their preferences. You can have a look first and play it through in your mind to see who would win this election, which of the alternatives would win the election. Have a quick check yourself. So it says down here, D wins. So let's check whether that's really true. We're running B against C. So there is Anne likes B more, and Cindy likes C more, but Bob also likes B more. So which one wins? B. So if I had a big pen, I would now write here B, but the good thing is I don't. So B against A, then A, B. There's one supporter for A, there's a second supporter for A. So A advances. And then we have A against D. A against D, one in favor of A, but the other 2 in favor of D. So D advances, so D wins the election. The Pareto principle said, if there are 2 alternatives, X and Y, everybody says X is better, Y should not win. Here we have, everybody says C is better than D, but still D was winning. So the cup rule, this cup rule, does not satisfy the Pareto principle. So for the people who are already a bit comfortable with some of the ideas that I've talked about, do you see the underlying reason for how I made this work in this example to get this very, very weird behavior? What's the underlying trick that I used there? How does it relate to anything that you've seen earlier today? How many people see it? Yes, so in the very back, let's do that.
It looks like it's a certain dependence. So you did the trick. So you kind of switched and put C preferable to B, like to left to left to left, and it means that for every person with advantages, it kind of looks like I don't know how to describe it, but there were always people for whom one choice was better than the other one.
Yes, very good. Yeah. So who knows the fancy word to say what he just said? Yes, it's a Condo Say paradox or a Condo Say cycle that we see here. So you talked about Condo Say, but not specifically about this. So if we think about the green stuff here as just being one blob, let's call it X, then this would be a very classical example of a so-called Condo Say cycle, where we have A, B, X, B, X, A, X, A, B, where for any 2 of you, so where there's a majority who prefers A over B, a majority preferring B over X, but also a majority preferring X over A. So the majority goes in a cycle, so there's no Condo Say winner. So it means whatever choice you made, there's always going to be a majority that wants something else. And I've embedded that here by making the X into a C and a D. So the Condo Say circular structure here ensures that because I very late entered the D, that whatever I entered late from the green stuff will survive. But I put the worst one of the two, so the bad one survives. So even though with respect to A and B, this is quite a good choice, with respect to C, it's a terrible choice. So this was kind of the trick. So this is really the Condo Say paradox raising its ugly head again that we see here. That's really the reason for why this is going wrong. Okay. I want to show you one more thing. I think it takes 2 slides, and then I want to take a short break. So one more example for a couple of axioms and thinking about what we can do with them. So the axioms that I want to introduce now, they're called anonymity and neutrality. So anonymity intuitively says all the voters should be treated the same. All the agents should be treated the same, symmetrically in some sense. And neutrality says we should be fair to the alternatives as well. All the alternatives should be treated the same. Now, I said on the slides, I want to keep it easy, so I didn't put a formalization on the slides, but you can formalize these kind of things. So do you have any ideas how you would go about formalizing this? Let's say anonymity. How would you go about? So how many people have an idea? Yes, please. All the voters should have the same impact, but is that a formalization or is this just a nicer way of saying what I just said, but still a bit hand-wavy? I think it's a nicer way than what I said, but it's still a bit hand-wavy. So how can we make it mathematically precise, exactly like that? Yes, please.
You can try to swap 2 people and see if the result is the same. And if it's not the same, then one is more important than the other. And then you don't have anonymity.
Yes, so you could say for any way of swapping 2 of the agents and for any profile of preferences, the outcome should not change. Yeah, that would be one way of saying it. I could even say more generally for not just for swapping 2 agents, but for any way of renaming the agents, the outcome should be the same. It's mathematically will be the same definition because of induction, blah, 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 never mind the details. So one, if you want to use fancy words, you would say for any way of permuting the agents, the outcome should not change. If you think of the voting rule as a function that has n entry points, in each one goes one of the preferences. If I take the same function, but with the input slots permuted, the outcome should never change. That would be a formal way of defining this. How about neutrality? How would I formalize neutrality? Yes?
So the same idea, but on the preferences, the name of the preferences, if I swap preferences names, I should get a swap, so a permutation.
So yes, so preferences, you mean alternatives. If I do a permutation on the names of the alternatives, then what should happen? So he's gonna finish your sentence. Then what should happen? Oh, no, I want to finish his. He's on the right way. So yes.
Result should have the same.
Very good. So now it's not that the result does not change. The result does change, but it changes in the same way. So if I look at all the preferences, and in the preferences I look at where the alternatives show up and have some permutation of swapping A with B, for example, and B with X. Whatever change I made in the input, the exact same change I should make in the output, and it should coincide. So that would be a way of formalizing this. So let's finish before the break with a couple of exercises. So this is about resolute rules now, what I'm going to talk about. So a resolute rule is one that always gives us a single winning outcome, a single outcome. This is what we want usually, right? So in general, you can imagine there could be ties. That's not very nice. We need to think about extra. So I want to focus now on rules that are resolute. And for the first, warm-up exercise. Give me an example for a rule that is resolute. Anyone has an example? Maybe one we've seen already, I don't know. Maybe one that you just invent in your mind. Yes. Dictatorship. What's a dictatorship?
We say, for example, the first voter decides who wins.
Yeah, so the first voter always decides who wins. That would be a terrible rule, but it would be resolute. So that's the one good thing that can be said about it. Okay. I don't like that rules, maybe. That's just me. But so are there other rules? Did you have a better one in mind?
Choice.
Random choice, but that's randomness is not really something that is part of our model at the moment, so I don't want to allow that. Give me an example that is not resolute, just to make sure it's clear in everybody's mind. What is difficult? What's an example for a voting rule that's not resolute? Yes? Plurality, for example, or border, or plurality with runoff, or anything that we've seen. It could always be that there's a tie. So most real rules with names, they can in principle have ties. So do you know how the ties are broken in the French presidential election if at the second round there's a tie? You do that in your constitutional classes when you're 10, I hope. No, is it? So what happens?
The youngest win.
I thought the oldest wins.
For the mayor, it's the oldest.
Okay, so it depends on the level of the election where it's the oldest or the youngest. So it sounds pretty crazy, but yes, they had to write it down somewhere. What's going to happen if that ever happens? Okay, so the boss says it's the older one. I believe him. Okay, so it's difficult to design these rules. Let's focus on them for the moment for the case where there are just exactly two voters and two alternatives. So quite a simple case. Exercise. So prove that, so for example, plurality does not work. There could be a tie, right? Maybe there's another rule. Exercise. Prove that there exists no rule that is both anonymous and neutral in this case that is also resolute. So think about this for a moment. What would you do? So let's call the alternatives A and B, for example, and the voters 1 and 2. How can you figure out that it's impossible to design a good voting rule in this setting in the sense that we want it to be resolute, anonymous, and neutral? Yes? So we need to have an exception. Yeah, so you're saying, so there could be a tie. We need to find a way to deal with this special situation to break the tie. It's clearly the right intuition. How can I cast this into a formal proof to really convince everybody in the room that there's no chance of ever designing a rule that's good? Yeah.
You said vector 1 prefers A and then B, and vector 2 prefers B and then A. And then the rule returns A, chooses A. It's not neutral because, I mean, it's either not neutral or not anonymous.
Yeah, yeah. So I think, right plan, let's start with a concrete problematic example. So plurality, border, they all would not know what to do in this case, so it seems a good one to start with. So suppose we have a profile where number 1 says A better than B, number 2 says B better than A. For the moment, suppose in this case the outcome were A. Our rule has to make some choice. Let's think what happens if the outcome is A, if the rule makes a choice A in this case. Now, let's look at a different profile where we swap the two voters. So now number 1 instead says B better than A, and number 2 says A better than B. So I have swapped the voters. So anonymity says that if I swap the voters, the outcome should not change. I should still have A winning, right? So if I make this choice, I must make this choice. Now let's go from here to here, but this time use neutrality. Neutrality means we are swapping the names of the alternatives. So if I swap the names of the alternatives here, this becomes A better than B, this becomes B better than A. Oh, look, it becomes exactly that thing over here. But also neutrality says, if I swap the names of the alternatives, I must swap the name of the outcome as well. So now it says, no, that's the wrong outcome. It has to be B. So contradiction, right? We made an assumption. We did 2 steps of reasoning. We got something else. That can't be right. So the choosing A was wrong here. I can choose B instead. I get the exactly same cycle. I get again a contradiction. So for the 2 possible choices I can make, it always goes wrong. So there is no choice I can make in this problematic profile that would allow me to to still have a well-defined voting rule in all cases. So resolute is very difficult. How about irresolute, meaning there can be some ties? What would be examples for rules that I can use for this special setting still? 2 and 2. This is the much easier exercise. No trick question. Maybe a small trick question hidden in there, but not a very bad one. An example, one rule that works. Plurality works, yeah. It's clearly anonymous. The people are treated the same. It's clearly neutral. The alternatives are treated the same. It's irresolute. Yes, there can be a tie, but it's a well-defined rule. Other examples. Plurality with runoff. Yes, very good. Is this really a different rule? In this case, not. How about border? It's also the same. So border and plurality with runoff, they're actually all the same rule here. The cup rule as well is the same rule because there's only one way of making a tree. So the rules we've seen, they all happen to be the same here, and they all are fine. Are there other rules that we haven't seen that maybe are a bit weird, but you could use as well? So how about instead of going with the majority, which is what all of these rules do, we go with the minority. We elect whoever is less popular. It's not such a good rule, but it is anonymous and neutral. So, right? So it also fits the bill. So we still have at least these 2 rules, the plurality, border, they're all the same, and this minority rule, maybe others that we can't think of right now. So we're not finished yet choosing. We have to add more axioms to identify a single rule. And now I want to take a break, and we take a break until, well, let's say I'm going to announce it as 5 minutes, and then I'll have you back in the room in 7 minutes or something. And then we'll start, and we're going to look deeper into that. How can we add an interesting axiom to these to actually get a single, clearly defined rule that we can say something about? So 5 minutes break, and I'll see you after that. Maybe I first ask whether there's anything from the first 45 minutes that I should explain again, or any questions about anything that we've seen. I put the break now because we're going to accelerate a little bit and do something a bit more complicated now. So let's have a look at that. So we've just seen before that if we are happy with irresolute rules, there are several rules that are anonymous and neutral in the special case of 2 alternatives and 2 voters. Actually, that's even true if we have 2 alternatives and any number of voters. The border rule is still the same as the plurality rule. It's still the same as plurality with runoff. And they're still, all of them, anonymous and neutral. So we have some evidence that this way of making choices when there are just 2 alternatives, as is done in this rule, might be the right one. It's somehow the only one that we could think of, except for this silly minority rule. But we would like to make that precise now. Is it really the right way of doing it? And can we say formally why we like it? And well, because there was still this choice between going with the majority or the minority, if we have a chance of saying exactly this is the right rule, we have to add some extra axiom to narrow the space down. And this axiom is what's called positive responsiveness. This is an axiom that says, if you're looking at a particular election and some alternative wins, if you change the preference of one of the voters to now also support that winning alternative that she didn't support before, it will still win. And it says a bit more, if we're in an election where there's a tie between A and B, both win. If we change one of the people who said B was better to saying now A is better, then the tie should be broken in favor of A, and A should now be the only winner. So that's positive responsiveness. Basically says more support is good for you if you're an alternative. That makes a lot of sense. So we can formulate it as an axiom. So all these different rules like border, plurality, runoff, in the special case of just 2 alternatives, they are all the same. And we usually use a different name for them. For this rule, we call it the simple majority rule. So that just says whoever of the 2 alternatives has more supporters wins. And if there's exactly the same amount of support, both of them win. That's the name. That's how this rule works. And this theorem from 1952 by Kenneth May, it says that if we're in the context of two alternatives and any number of voters, if you want a rule that is anonymous, treats all the voters the same, neutral, treats all the alternatives the same, and positively responsive, rewarding additional support, then we must use the simple majority rule. The simple majority rule has these properties, and it's the only rule in the universe that has these properties. So if this theorem is true, as we're going to check in a moment, then that's quite useful, because it's quite difficult to argue, if I come here tomorrow and say the majority rule is what we should use, okay, you maybe believe it because you heard it before, but if I had to say exactly why I like it, would be really, really difficult to explain that. Having this characterization theorem says, I can split my explanation, my justification for why it's a good rule into three parts. I first convince you about anonymity, maybe in isolation, that's an easier task. Then I convince you of neutrality. Again, that's an easier task. Then I convince you of positive responsiveness, a bit harder, but still easier than justifying a full rule. And then I refer to the mathematics on the board and say, and therefore that's the only rule that's left, so you must accept it. So it's very useful for figuring out what we actually want to do by kind of splitting down the rule into its constituent properties, these axioms. Okay, so but now we want to prove this. And the exercise at the bottom of the slide says there are two directions in this theorem, if and only if. So there's this direction and that direction, left to right and right to left. It says one of them is pretty easy. Which one is it? Let's do first that, and then how would you prove it? So which one is the easy direction? Left to right or right to left? Right to left. Right. If it's the majority rule, it has these properties. That's easy to check because we have a concrete rule to think about, and we just have to tick off the three properties one by one. So let's tick them off. Is it anonymous, and why? Anybody can say why it's anonymous, the majority rule? Yes? Yeah, if we swap two voters, it doesn't change the outcome. So no voter has any special role in there. It just matters how many people want something, but not who they are. Yes, very good. Neutrality. Why does it satisfy neutrality? So remember, we have just two alternatives here. So let's call them A and B from now on. Why is it neutral? For each permutation, you have let's say the corresponding result. Yes. So none of the more intuitive explanation is none of the two alternatives has any special status. It just matters how many people want it. And if we have a concrete outcome and we swap everybody's preference, the A for the B, we also swap in the outcome, the A's and the B's. Yeah, so it is neutral. And positive responsiveness. Why does it satisfy positive responsiveness? What do we have to think about to check that? Yeah. So, yeah, so if there's a tie, A and B are doing equally good, and then we change one of the people who previously voted for B, now voting for A, then A wins with 2 points advantage, right? So it breaks the ties. And even easier if A is already winning and one more person also wants it, of course, it also still wins. So yes, it satisfies the properties, but the other direction is tricky at first, right? It's not obvious how you go about proving something like this, because it just says it has to have this and this and this property in this huge space of potential functions that I could define as rules. Why is there only one left? It's not clear how to set up a proof to do this. I mean, intuitively, you could say, oh, I can't think of another rule that does the job, but that's not a proof, right? You may have just not seen it. So indeed, if I had not mentioned positive responsiveness, we might have convinced ourselves wrongly that the theorem works even with anonymity neutrality, and it doesn't, because the minority rule is a counterexample. So how can I be sure that I haven't overlooked another counterexample? That's what we have to check. So I have a proof on the next slide. On the top, I'm repeating the theorem that we're trying to prove. We've proven one direction already just now with our hands. So the rule does have the three properties. Now we are going for the other direction. That is the interesting one. I will only prove the case where the number of voters is odd. Where the number of voters is even is very, very similar and not more difficult. So I'm not wasting your time with that here. Let's just assume for now the number of voters is odd. This is enough to understand the basic ideas. So it helps a little bit if the number of voters is odd. There are never a tie in the majority rule. So that simplifies it a little bit to think about, but mathematically it's basically the same if they are even. So our alternatives are little a and little b. And the big A and the big B, let's big A be in a specific situation, the set of voters who prefer A, who submit this, and let big B be the set of voters who submit that, who prefer B. Right? So this is just a more compact way of thinking about a profile. Let's first use the anonymity axiom. Anonymity says, treat all the voters the same. What this basically means is that the only thing that decides what the outcome is the number of elements in A and the number of elements in B. It should not matter who sits in A and who sits in B, but just how many are in there. So the cardinality of these two sets, our rule has to be definable in terms of some kind of rule that looks only at the cardinalities of these sets, not really looks inside of the sets. That's what anonymity basically means. So now I've used anonymity and I've simplified the space in which I have to look for a rule. It has to be a rule that has to be definable in terms of these numbers, the cardinalities of the sets. And now I'm going to a case distinction. And the case distinction will be the following. The first case will be the right case. So this will be stating a feature of the rule we're looking for that obviously should be true. And the second case will be a case that I will later show leads to a contradiction, so can't actually ever happen, but mathematically we have to take care of it. So the case distinction is the following. It could be that whenever there's exactly one more A supporter than B supporter, then only A wins. So the majority rule, for example, does this, but I'm not sure yet it's the majority rule. So, but let's assume this, we could assume that's the case. Or we could assume that that's not the case. So there at least exists at least one scenario where there's exactly one more A supporter than B supporter, but nevertheless B wins, maybe alone or maybe in a tie with A. So I have to consider both cases. I will in the first case prove if this is known to be true, then actually it must be the majority rule. And in this case, I will prove if this is happening, then actually we read the contradiction, so this can't be happening. So we are left with the rule that we want. So this would be the high-level structure of the proof. So now let's do the first case. Suppose all I know about the rule is if there's exactly one more A supporter than B supporter, then A is the only winner. I don't know anything else about the rule so far. It's consistent with majority, but it doesn't define majority yet. How can I get majority? First, I'm going to use positive responsiveness, which says if you increase the support for a winning alternative, it will still win. And I can apply it once, or I can apply it several times. If I do that, I find out that not only if there's exactly one more A supporter than B supporter, but in general, if there are any number of more A supporters than B supporters, A must be the only winner. So by positive responsiveness, A still is the only winner if there are 5 or 17 more A voters than B voters, any higher number. This follows by just one by one switching the B supporters to A supporters until I get this kind of scenario that I'm interested in right now. Okay, this covers already quite a lot of ground, but still not everything. Now we're going to use neutrality, and it says that if it's the other way around, if there are strictly more B supporters than A supporters, then now B must win. If we switch everybody around, we also must switch around the result. And now, because it's an odd number of voters, we've covered every possible case. Either there are more A supporters, or there are more B supporters. In both cases, we know what the outcome will be. In both cases, it coincides with what the majority rule would do. So we have reached the majority rule. We might call this rule border. We might think of it as defined like a border rule or as like defined as plurality with runoff. But what it actually does is what the majority rule does. So it is the majority rule. So in this case, if this assumption is true, the theorem is true. But it could still happen that the assumption is false. And there exists at least one counterexample of sets of A and B supporters with one more A supporter and still B is a winner. So I have to get a contradiction to get rid of this problem. So let's look at this situation, one more A supporter. And now let's suppose one of the A supporters switches to B. So if before B was at least one of the winners, if now it gets a bit more support, it will now become the only winner. So now we have a situation A prime, B prime, where there's exactly one more B supporter. And we now know that B is the only winner. So this situation and that situation, they're symmetric to one another by swapping the names of the alternatives. So if in this situation, I swap the names of the alternatives, by neutrality, now A should be the only winner. But then I have a contradiction because first I assume B is a winner. Now I have A should be the only winner. This can't both be true. So I have the contradiction that I wanted. And I know that the second case is actually impossible. Which is what we expected, right? Because it sounds crazy that there's exactly one more A supporter and B supporter, nevertheless B wins. It doesn't sound right. And we made it explicit where the problem is. It contradicts positive responsiveness together with neutrality. We get a contradiction, so we get rid of this case. So that finishes the proof. Any questions about this? No, I do not assume that the rule is resolute. So actually I get here, in the case of an odd number of voters, which is only the case that I proved here, as a side effect, I happen to get resoluteness because the majority rule is resolute if the number of voters is odd. But if it's even, it's not resolute, and the proof would look slightly differently, but it's almost the same thing. If you write it out, you get almost the same thing. Okay. So the majority rule is nice. The simple majority rule is nice, but it's only, this theorem only applies for two alternatives, so it's not very general yet. I'll show you one more thing very quickly about what is nice about this rule. That one is not axiomatic method. This is the epistemic part. This idea that suppose there's an underlying ground truth, which voting rule works well. So imagine what would be a scenario. There are two vaccines, and we're asking 100 doctors which one is better. They are educated people, you know, they know their stuff, but they do also make some mistakes. And suppose that each of them is only right with 55% of the cases that we ask them a very difficult questions such as this. So we wouldn't want to rely on a single person to advise us on something important like this. But let's say we ask 100 and we have to aggregate the opinions somehow. They disagree with each other a little bit. We're using a voting rule with two alternatives to choose. And the doctors are the voters. Which voting rule is the right one? Which one maximizes the probability of making the right choice if we implement the outcome of the vote? That would be the epistemic view on social choice theory. And there's this classical result by Condo Say from 1785, who at that time already understood something that nowadays would be considered pretty obvious, but it was not at the time. If I have an election with two alternatives and n voters, one of the two alternatives is the right one. Every voter has probability P of correctly identifying it. And P is maybe small, but greater than 1/2. So maybe 51%. Then the simple majority, the probability that the simple majority is right will increase monotonically as we increase the number of voters. And it will, in the limit of an infinite number of voters, it will go towards 1. So if we have a really high number of voters, we are almost always taking the right decision if we go with majority. So that's another nice property of this rule from a very different perspective. If you want to formally prove it, this is basically the law of large numbers, which says that in this case, so even if you're only 51% of the time right, if we have 1 million people, it will really be almost exactly 51% of the population who give the right answer and almost exactly 49% who give the wrong answer. So majority will get it right. If I only ask 10 people, you know, I might sometimes not have you know, just 6 people getting it right. So it will be a little bit wrong. So then it's more risky, but if we have enough voters, it will almost always be right. So it's a pretty good rule. So just very quickly to show you, there are also other ways how I can decide what rule to use, but it's still only for two alternatives. So now I want to move on to the case where there are more alternatives. So for example, the border rule was a very nice rule, seemed a very nice rule for doing this, but it seemed a bit specific to use the numbers 9, 8, 7, all the way down to 0. So somebody said, I like the Eurovision contest. I like those numbers more. So why should I not use the Eurovision contest numbers rather than the border numbers or some other sequence of numbers? So people have thought about this. There's a whole family of rules called the positional scoring rules, where border and Eurovision and what else you like are part of. And they are defined as follows. Remember, we have m alternatives. So we're going to write a number for, we're having m numbers, S1 to Sm. S1 is the score you get from a voter if you're on position 1. S2 is the score you get if you're on position 2. Sm is the score if you're in the last position. So border would be like m-1, m-2, m-3 down to 0. Eurovision would be 12, 10, 9, 1, many zeros. I think that's still the rule. And so we don't require very much of these numbers. We just require that they are weakly decreasing. So you shouldn't get more points if you're further down the ranking. And we say that the first one should be really strictly more than the last one. So in Eurovision, there are lots of zeros at the end, so it doesn't have to be strictly decreasing. But the very first one, the 12, is strictly more than the 0 at the bottom. So this is a family of rules. The border is an example. Plurality is an example. Plurality is the positional scoring rule with the vector 1, lots of zeros. It's a bit complicated, but I can think of plurality in these terms. Another rule is called anti-plurality, or sometimes called the veto rule. It's lots of ones and then a 0. So that basically means you get a point as long as you're in the last position. So you are electing something that is not really, really unpopular with many people, something like that. There are also the K approval rule. So for example, K might be 3. That means you get 1 point if you're in the top 3 positions, you get 0 otherwise. Exercise. There's a rule that is characterized by this vector, 9, 7, 5. So there are 3 alternatives, and the scores are 9, 7, 5. Do you know this rule? What's the name? I think you have heard of it. Think about it for a moment. So the scores are 9, 7, 5 for the people who can't read it at the back. What's the name of this rule? It's quite a famous rule, actually. Quite famous. So I didn't understand what you said, but it's good because I first want to hear, like, how many people, just, you don't have to say anything, just raise your hand if you think you know the rule. Yeah, 2 people, it's not enough. I'm quite convinced that you know the rule. Why am I so convinced that they know the rule? Exactly, because I just told you about the rule. You all know the rule because I told you about the rule. It's the border rule. So why is this the border rule? Can you explain why it's the border rule?
So it's the same up transition and multiplying by a positive constant.
Yes.
It doesn't matter if I start at 0 or at 5, and it doesn't matter if the unit is 1.
Yes, very good. So let me repeat that. So the border scores, they would be 2, 1, 0. And here instead I have 9, 7, 5. So if I multiply by 2 here and add 5 to each of these numbers, I get that. So imagine a border election, and I multiply everybody's score by 2. Then the scores change, but the winners don't change, right? You just have, everybody has twice as many. Then I add everywhere 5 for every voter. Again, the scores do change, but the relative ranking does not change. It's still the same winner. So these are 2 different representations of the same rule. And just, 2, 1, 0 looks a bit cleaner, nicer, more convincing, but it's the same rule. Question?
Yeah, just a quick when using the border rule, do you necessarily need to have the grades that are fully spaced?
Yes, when I have the border rule, I do have grades that are equally spaced. So for example, if I had 3, 1, 0, where's this rule used?
Football.
In football, exactly. So you win again, you get 3 points, you draw, you get 1, you lose, you get 0. That's not the same rule, because here, that's why they changed it in 20 years ago or something like this, because it was boring, because they were always just drawing. And then they made it a bit more, making a win really more important, more impactful. So now, when before, let's say there was somebody was winning 1 game, the other one was drawing 3 games, they were equal, they would be equal here. Under border rule, the one that's drawing 3 times would be better than the one that's only winning 1 game. So they are not the same rule, yeah. But so these are not the same rule, these are the same rule. Okay, so the idea here is that you have to be a bit careful about what you really mean. There could be more than one representation of the same rule. So now we've seen before the example that border does not satisfy Condo Say, so maybe the Eurovision rule does it, or maybe the football rule does it, or maybe some other rule does it. And unfortunately, the answer is no. As I will prove to you on this slide, there is not a single positional scoring rule, even though there are so many of them, that satisfies the Condo Say principle. Very surprising, very sad as well, but good to know. So let's have a look. Example with 7 voters and 3 alternatives. A is the Condo Say winner, I say here, so let's just check. A against B, 4 people, so yes, it's a majority. A against C, 3, 4, also a majority. So yes, A is the Condo Say winner. So A should win under Condo Say, according to Condo Say. Let's look what an arbitrary positional scoring rule would do. And I will show you that B must win. So what would an arbitrary positional scoring rule do? How many points would A get? It would get, by the scoring rule is defined by S1, S2, S3. So A would get 3 times S1 points from here. Am I doing the right thing? And 2 times S2 points from these 2 people, and 2 times S3 many points from these 2 people. So this would be the sum of points that A gets. And let's do B as well. So 3 times 3 people put it in the first position, 3 people put it in the second position, and 1 person puts it in the last position. And and C, I can also write it down. So C has no chance, I think that's clear, but let's understand A and B relative to each other, how they do. We don't know right now what S1, S2, and S3 should be. We're still free to choose nice values, but whatever we choose for S1 doesn't really matter because both of them get the same time, 3 times S1. So it's irrelevant what I put here. I can ignore it. So then the difference here is 2 times that and 2 times that, or 3 times that and 1 times that. So the difference is that B gets 1 more times S2 and A gets 1 more times S3. And the rest of the sum is the same. So B gets an extra S2 and A gets an extra S3. But we know by definition that S2 must be at least as much as S3, and in many cases will be even strictly more. So then this marginal thing that B gets is better, or at least as good as the marginal thing what A gets. So B must always either strictly beat A or at least draw with A. So while the Condo Say axiom says only A should win, this constraint on the score set, B must be amongst the winners. So we have a contradiction, so it can't work. Again, a very quick excursion into a different part. Let me do this very quickly and without reading it out in detail. So there are also some rules that are maybe interesting. For example, this Dodgson rule is a rule that satisfies the Condo Say principle, while border and the other position scoring rules do not, but it have other problems. So this one has the problem that it's highly complex to compute the outcome. So the rule says something like, if there's a Condo Say winner elected, if there's no Condo Say winner, check for each alternative, how many little changes do you have to make to the preferences before it becomes the Condo Say winner? And you elect the one that requires the fewest of these changes. And you can imagine really this kind of quite a combinatorial problem. It's not obvious how you would design an algorithm to do that. And indeed, it turns out to be very difficult, even worse than NP-hard. There's something called NP completeness with respect to parallel access to NP. So that's in the complexity theory hierarchy a little bit above NP. And so this is a problem that is hard with respect to this horrible class. So even though maybe for other reasons I might like this rule, this would be a problem with it. So this would be really the heavy algorithms kind of perspective on social choice. So the last thing I want to do today, I want to talk a bit about the strategic manipulation problem. We've seen it, a glimpse of it already with the abstention thing, so that sometimes it was good for people to not show up for the election. And plurality with runoff had this problem. The other rules that we've seen do not have this problem, so it's not such a big problem for other rules. But there's a related problem, is this manipulation thing, that you sometimes are better off by lying about your preferences. So let's look at this example. So maybe some of you remember or have heard about, in 2000, there was the presidential election in the United States. It was very close. There was Bush, the Republican, the young Bush, the Republican candidate. There was Al Gore, who was the Democrat, and Ralph Nader, who was the kind of, in American terms, like crazy antichrist, left-wing communist, like here would be average Labour Party kind of person. But in the American context, this is like an extreme choice. And it really boiled down to what happens in Florida. The rest, so if Florida goes for the Democrats get it. If it goes for the Republicans get it. There was lots of horrible stuff happening, probably with with court cases. I mean, nowadays we think this is normal, but even worse maybe nowadays. But at that time, this was a major shock. And I'm going to idealize it a bit and say, suppose none of the cheating happened, of the officials. Suppose it was more or less like this in Florida. 49% preferred the Republican candidate. 40% preferred the Democrat, but they were split on whether they like Nader or Bush more. And 11% like Nader more. And then, of course, they like the Democrats in the middle and then Bush. And let's say there's no other kind of people. And they use plurality over there. So Bush wins fair and square in this election. 49 is better than 40. 20 plus 20 is certainly better than 11. So Bush wins. And then you could say to the Nader voters, and people have said it to them, you silly people, this was predictable. You should not have gone with your favorite choice, Nader, who had no chance of winning anyway. You should have voted for the moderate candidate, Democrat. Like, a few years ago, that would have been, you should have gone for Hillary Clinton or something like this, or for Joe Biden. And this time it worked with Biden, but you should have done that rather than what you really believe in, because you had no chance of getting what you want anyway. And you could make that argument, and we would maybe be living in a better world today if they had made that choice at the time. But is it fair to blame the voters for that? Or should we not rather blame the voting rule? It's not nice that the voting rule forces people to make this choice. Should I be truthful about what I really think is right and report it to the rule? Or should I be strategic and just think, and tactical, and I can't get what I want really, so I'll do this compromise and so on. And then if everybody does this, do the preferences we collect, do they really still mean something? Maybe not. So it would be nice if we had a rule that doesn't have this problem. So can somebody tell me about a rule that is better than the plurality rule in this respect that does not have this problem? Anyone who has a suggestion? Yes.
Transferable vote.
Yeah, single transferable vote, like they use in Australia, for example. It's the wrong answer. Too difficult to explain now. Yes. Yes. Yes, you. Yes, definitely you. Yeah. Yeah, for this particular example, many other rules would not have this problem. So plurality runoff is in a way designed to deal with examples like this, but it's also not true in general. There are other examples where it goes wrong, unfortunately. Any other ideas? Yes. Condo Say rule, meaning what exactly? Yeah. So you win if you're the Condo Say winner, if you meet anyone else in the Paris contest. And what if you don't? If nobody is the Condo Say winner, what do you do then? Yeah, random is not allowed. Random is not allowed. That also would not go down well with the voters. We say, and in 20% of the elections, we just choose randomly. Doesn't go down so well. Yes?
The one where you count only the least preferred and We start with
Yeah, that's a single transferable vote that you said, yes. So it doesn't work, unfortunately. I don't have a nice, easy example. It's difficult, but I know that it doesn't work, yes.
scoring the candidates.
Scoring the candidates, like in border, for example, or differently.
Voters attribute grades.
Okay, giving grades, but then we are like, this is a bit like the probability idea. We're moving outside of our model. So right now we say preferences are rankings. You have to give a ranking. We don't assume that people in their mind are able to assign numbers to voters. This is a bit of a, I mean, very strong assumption that that would be possible, that I can number or grade my candidates. I want to only say I can rank them. Sebastian? 5 minutes. Yes, we'll be done in 5 minutes. Yes. Okay, so he said we have to finish in 5 minutes. So last suggestion very quickly.
I don't know if it applies here, but median voters.
Yeah, it's also something with the grades. And I think so. No, so the bad news is that all your solutions are wrong. And I don't even have to think about it because I know this theorem that says all of the solutions are wrong. It says it's impossible to design a reasonable voting rule that does the job. The only exception are dictatorships. So what the theorem says is the following. I want a resolute rule. I want a subjective rule. What this means is every alternative wins in at least one profile. So for example, if everybody wants A should win. That would be crazy if that were not the case. So these are very basic things. I wanted manipulation to be impossible. There should never be a situation where somebody gets an advantage by lying. Then it says, yes, that's possible. There are exactly N rules that do the job. And these are the N dictatorships. The first voter could be the dictatorship. The second voter could be the dictatorship. So a dictatorship means we just take the vote of the dictator and copy over the most preferred alternative. And that's the outcome in every possible situation. So that rule does have these nice properties, but it's of course a very bad rule. And the theorem says there is no other rule that does the job. Quick question?
That's the link to our theorem.
There's a close link with Arrow's theorem, yes, which also has dictatorships with it. So you can derive one from the other with a little bit of work, goes in both directions. And this also, I should have said, this is true for 3 or more alternatives. There are just 2 alternatives, it's okay. Simple majority is wonderful, but for 3 alternatives, it's not okay. So this is a really, really bad, really serious issue. I have not completely finished what I want to do tomorrow, but probably will show up tomorrow again, and we'll try to understand it a little bit better tomorrow. The last thing I want to show you today is that one way of that has been proposed for getting around this is to say that, okay, manipulation is always possible in principle, but maybe we can really make it difficult for people to manipulate. So maybe we can make a rule that is where it's computationally hard, maybe NP hard or something like this, to do the bad thing. That would be nice. And then the single transferable vote that somebody mentioned, the rule that they use in Australia, that one has this property. That's the theorem mentioned on the slide. It can be manipulated, but it's really difficult to manipulate. So that's a bit better than plurality or plurality runoff, where it's easy to manipulate in certain situations. This was a very popular topic in computational social choice 15 years ago. Since then, has fallen a bit out of favor because people think, well, it's NP hard means in the worst case. But we're going to have one election every 4 years. You know, people have enough time to power up their big computer. So maybe theoretical hardness result is not really going to get around the problem in practice. So one has to be careful about these results, but I think they're very interesting. They show nice connections between computer science and voting theory that you would not have expected 20 years ago, a bit more than 20 years ago, 30 years ago, sorry, before they started thinking about these things. So I think it's cute, nice, interesting results. We have to be a bit careful about how useful they are in practice. And in practice, there really is an issue. Okay, last slides to conclude. So what I've done today, I started talking a bit about computational social choice. So in general, it's about you get different views from people, from agents. You aggregate it into a global collective view. Voting is an example, maybe the most important example of this, where views are rankings of alternatives, and we have to get the best alternative. I've shown you examples for concrete rules, so plurality, border, and so on. I've shown you examples for concrete axioms like anonymity, Pareto, and so on, that are properties that we care about in voting rules. And I've shown you examples for results that show, in the case of May's theorem, for example, look, this is a good rule according to these axioms. Or Gilbert-Satterthwaite, the last theorem, that says, look, there is no good rule according to these axioms. And then I also showed you many examples like this rule satisfy or does not satisfy this particular axioms, which is a bit less exciting mathematically, but concretely tells us still useful things about how to do things. This week, you're just going to learn about a tiny part of computational social choice. So there's the handbook of CompSoc, which this is a page where I have the slides of the two talks. And there you can download the book, or you can also easily find the book online if you want to learn about many more things. And that's it. Now I see you tomorrow again. Thank you very much.